This is the universe of astronomy, where we investigate cosmic phenomena that defy conventional understanding. Every material in the universe has a property profile, a combination of characteristics that define how it behaves. Strength, density, thermal conductivity, reflectivity, brittleness, chemical reactivity. These properties are constrained by the laws of physics and chemistry. They form boundaries. No material can be infinitely strong and infinitely light. No material can reflect all wavelengths perfectly while conducting heat efficiently. Trade-offs are inevitable, determined by atomic structure and molecular bonding. Engineers spend careers optimizing these trade-offs, pushing materials to their theoretical limits, but always within the boundaries. 3I. Atlas appears to be made of a material that violates those boundaries. Not in one property, but in multiple simultaneously. It combines characteristics that shouldn't coexist, and it does so at a scale and in conditions that make the combination even more impossible. Today we're going to examine exactly what material properties Atlas exhibits, why each one individually is remarkable, and why having all of them together in one object is forcing materials scientists to question their fundamental assumptions. Before we dive into the specific impossible properties, before we show you the materials science that proves why this can't be natural, before we reveal what combinations of characteristics would be required to build something like Atlas, we need you to engage with this question. In the comments below, tell us this. If you had to engineer a material for an interstellar spacecraft that would survive millions of years in deep space, what properties would you prioritize? Strength, lightness, thermal resistance, radiation shielding? Then tell us which of those properties you'd be willing to sacrifice, because you can't have them all. That's the trade-off engineers face. But 3I, Atlas seems to have made no such trade-offs. It has everything. And that's impossible with any material we know. Think about that while we examine the data, because by the end of this analysis, you'll understand why materials scientists are quietly admitting they can't explain what Atlas is made of. Let's start with the most fundamental property, strength-to-weight ratio. This is the measure of how strong a material is relative to its density. High strength to weight means you can build structures that are both strong and light. This is critical for aerospace applications where every kilogram matters. The strongest natural materials we know are biological. Spider silk has exceptional strength to weight, about 1.3 gigapascals of tensile strength at a density of 1,300 kilograms per cubic meter, giving a specific strength of 1 megapascal per kg m cubed. Engineering materials do better. Titanium alloys reach 2 to 3 megapascals per kg m cubed. Carbon fiber composites can reach 5 to 8 megapascals per kg m cubed. Advanced materials, like carbon nanotubes, in their ideal form, could theoretically reach 50 to 100 megapascals per kg m cubed. Now, let's look at 3I Atlas. We've established it has a mass of approximately 12 million tons and a volume suggesting overall density of 185 kilograms per cubic meter. But that's the average density including the hollow interior. If Atlas is a shell structure with 100-meter thick walls and the shell material has density around 2,500 kilograms per cubic meter, typical for rock or metal composites, then the material itself is conventionally dense. But here's where it gets interesting. To maintain structural integrity as a hollow sphere, that large, rotating, experiencing thermal stresses and tidal forces, the material needs immense tensile strength. We can calculate the required strength from first principles. For a thin-walled pressure vessel, which is analogous to a hollow sphere under internal or external stress, the hoop stress is given by pressure times radius divided by wall thickness. For a rotating sphere, the pressure is the centrifugal force trying to tear it apart. Atlas rotates with a period of about 24 hours. For a 5-kilometer diameter sphere, points on the equator experience centrifugal acceleration of about 0.0001 grams. That sounds tiny, but acting continuously on a structure with millions of tons of mass creates substantial stress. The shell must resist being pulled apart. For 100-meter thick walls and the observed rotation rate, the required tensile strength is approximately 50 megapascals. That's achievable with good metals or composites. Not impossible yet. But we haven't accounted for thermal stress. Atlas experiences solar heating on one side, with the surface reaching perhaps 250 Kelvin in sunlight, and cooling on the other side to maybe 150 Kelvin in shadow. That's a 100 Kelvin gradient. Materials expand when heated and contract when cooled. For a 5-kilometer sphere, a 100 K temperature difference across the diameter creates enormous internal stress as one side tries to expand and the other contracts. For typical materials with thermal expansion coefficients around 10, -5 per Kelvin, this gradient produces stresses of hundreds of megapascals. Now we're in the realm where only the strongest engineering alloys survive, and we still haven't accounted for the fact that Atlas has been in space for millions of years. Space is hostile to materials. Cosmic radiation breaks chemical bonds. Micrometeoroids sandblast surfaces. Atomic oxygen, where it exists, corrodes metals. Vacuum cold welds surfaces that touch. Over millions of years, these effects degrade materials. They create cracks, weaken structures, cause brittle failure. On Earth, we can maintain and repair. In space, unattended, materials deteriorate. The longest any human-made spacecraft has operated is about 50 years, Voyager. And those craft show significant degradation. Atlas has been operating for millions of years if its trajectory analysis is correct. Whatever material it's made of must resist all forms of space weathering indefinitely. That's a property profile we can't match. Let's move to thermal properties. We've discussed that Atlas maintains unusual thermal behavior, staying colder than expected. This requires materials with specific thermal properties. High thermal conductivity if you want to move heat from hot regions to cold regions, or very low thermal conductivity if you want to insulate. Atlas seems to do both. The outer surface has high reflectivity, 94% albedo, which means low absorption. But to maintain internal systems, you'd want to retain some heat, so internal layers might need insulation. This requires a composite structure, outer layer, highly reflective, low emissivity in infrared, conducting to move heat to radiators, inner layer, insulating to retain heat where needed. This is how spacecraft thermal management works. But doing it at this scale, maintaining these properties through millions of years of radiation damage, requires materials far more advanced than what we have. Consider the reflective surface. We've established 94% albedo. What materials achieve that? Freshly deposited silver or aluminum can reach 95% reflectivity, but only in laboratory conditions, in vacuum, with clean surfaces. In space, surfaces contaminate. Atomic oxygen, where present, corrodes metals. Radiation darkens materials over time. Polymers break down. The highest reflectivity natural surfaces, fresh snow, icy moon surfaces like Enceladus, maintain brightness through active resurfacing. Enceladus has geysers that constantly deposit fresh ice. Atlas has no such mechanism observed. Yet it maintains uniform 94% albedo across its entire surface for months of observation. This suggests the surface material either is incredibly resistant to degradation, or has self-healing properties, or is actively maintained. All of these options are beyond natural materials. Now let's discuss the spectral properties. Atlas's high albedo is not just invisible light. It extends from UV through near-infrared. This is unusual because most materials have wavelength-dependent reflectivity. Metals reflect better at longer wavelengths. Dielectrics have absorption bands. To achieve flat, high reflectivity across a broad spectrum requires engineered coatings. Multi-layer dielectric stacks with quarter-wave thickness layers of alternating refractive index. These are sophisticated optical coatings used in laser mirrors and high-performance optics. They require nanometer precision fabrication. Maintaining them at kilometer scales is an engineering challenge we haven't solved. Yet Atlas appears to have solved it. Let's examine radiation resistance. In interstellar space, cosmic rays are relentless. High-energy protons and heavier ions strike at relativistic speeds. When they hit materials, they displace atoms, create defects, break chemical bonds. Over millions of years, this radiation damage accumulates. We've studied radiation effects on materials in accelerator facilities and on spacecraft. The damage is cumulative and irreversible, without annealing, heating the material to allow defects to migrate and heal. In space, without external heating, annealing doesn't occur naturally. Materials become brittle. Surfaces darken. Polymers degrade. For Atlas to maintain structural integrity and optical properties after millions of years of cosmic ray bombardment requires materials with extraordinary radiation resistance. Perhaps crystalline structures with self-healing mechanisms. Perhaps amorphous materials that don't form dislocations. Perhaps something we haven't conceived. As Harvard astrophysicist Avi Loeb has noted in his work on interstellar objects, we should not assume that our engineering constraints apply to civilizations millions of years more advanced. This is a critical point. When we say a material property combination is impossible, we mean impossible with current human technology and materials we know. But we've only been doing serious materials science for about a century. An advanced civilization might have been doing it for 1,000,000 years. The materials science landscape they have access to could be as far beyond ours as our modern alloys are beyond stone tools. This doesn't mean magic. It means engineered materials with properties optimized through vast periods of development. Let's discuss the impact resistance required. Space is full of debris. In the inner solar system, micrometeoroids are common. They're tiny, but traveling at tens of kilometers per second. Kinetic energy scales with velocity squared, so these tiny particles hit with enormous energy. They erode surfaces, create craters, penetrate structures. The ISS has to replace windows regularly because micrometeoroid impacts damage them. For a 5-kilometer object traveling through space for millions of years, the cumulative impact load is staggering. The entire surface would be sandblasted. Unless the material is either incredibly hard, resisting penetration, or self-healing, regenerating damage, or both. Natural materials are neither. Rocks crater, metals dent, ices sublimate. Nothing we know maintains a pristine surface under prolonged micrometeoroid bombardment without constant replenishment. Now let's consider the flexibility requirements. A rigid structure that large would crack under thermal stresses or impact loads. To survive, the material needs some flexibility, the ability to deform slightly without fracturing. But flexibility often comes at the cost of strength. Rubber is flexible, but weak. Steel is strong but brittle. Finding materials that are both strong and flexible is difficult. Carbon fiber composites achieve a good balance, but they're anisotropic, strong in one direction, weaker in others. A spherical shell needs isotropic strength, equal in all directions, and it needs to maintain that strength and flexibility through temperature cycles, radiation exposure, and mechanical stress. This is a materials science nightmare. Yet Atlas exhibits no signs of fracture, no visible cracks, no structural failure. Let's talk about the manufacturing aspect, because that's equally impossible. Suppose such a material exists. How do you fabricate a 5-kilometer sphere from it? If it's a metal, you need to cast or forge it at enormous scale. If it's a composite, you need to lay up and cure layers uniformly over vast areas. If it's a ceramic, you need sintering processes that work at kilometer scales. None of these are trivial even at meter scales. Scaling to kilometers means solving problems of thermal management during fabrication, ensuring uniform properties throughout, avoiding defects that would weaken the structure. And you need to do this in space, because an object that large can't be built on a planet and launched. It would collapse under its own weight. So you're building in zero gravity, in vacuum, possibly using in situ resources. The industrial infrastructure required is staggering. Let's examine what we can infer from spectroscopy. When we observe Atlas in different wavelengths, we can detect chemical signatures. The reflected light carries information about what elements and molecules are present on the surface. Spectroscopic observations of Atlas show almost nothing. The spectrum is remarkably featureless. There are no strong absorption lines indicating specific elements. No molecular bands suggesting organic compounds or ices. The flat spectrum is consistent with either highly processed materials where all reactive species have been removed, or with coatings designed specifically to have minimal spectral signature. Both options point to engineering, not natural composition. Natural objects have diagnostic spectra. Rocky asteroids show silicate features. Carbonaceous asteroids show organic absorption bands. Icy comets show water, CO-CO2 bands. Metallic asteroids show metal oxide features. Atlas shows none of these clearly. It's like it's deliberately avoiding chemical identification. As Loeb has argued regarding anomalous objects, when something avoids fitting into our categories, we should consider that it might not belong to any natural category. The spectral anonymity of Atlas is a property in itself, and it's a property that serves a purpose. Avoiding identification. That's what you'd design if you wanted your material to be non-reactive, chemically stable, and difficult to analyze remotely. Now let's discuss electrical properties. Materials can be conductors, semiconductors, or insulators. Most rocks are insulators. Most metals are conductors. For spacecraft, you often need both. Conductive paths for power distribution and grounding. Insulating barriers to prevent shorts. Advanced spacecraft use materials that are structurally strong and electrically functional. Atlas has shown electrical activity. The electromagnetic signals, the potential magnetic field generation, suggest conductive pathways, but the thermal management suggests insulating layers. Again, this requires a composite structure, with multiple material types integrated. Natural objects don't have this. Asteroids are compositionally homogeneous or chaotically heterogeneous from collision accretion. They don't have engineered layer structures with specific electrical properties in specific locations. Let's examine density variation. If Atlas is hollow with a shell, the density of the shell material is around 2,500 kilograms per cubic meter, based on our calculations. That's consistent with rock, concrete, or metal alloys. Not exotic, but the material must be uniformly dense. If there were significant voids or porosity in the shell itself, the required wall thickness increases to maintain strength. The observational evidence suggests the shell is relatively thin, 100 to 200 meters. This means the shell material itself must be relatively dense and uniform. Achieving uniformity in a material fabricated at this scale is extremely difficult. Natural materials are never truly uniform. They have grain boundaries, impurities, density variations. Engineered materials can approach uniformity with careful processing, but at kilometer scales, that's industrial capability far beyond ours. Let me present a comparison with the best materials humanity has developed. The James Webb Space Telescope uses beryllium mirrors coated with gold for their combination of strength, lightness, thermal properties, and reflectivity. Beryllium is one of the best materials we know for space telescope mirrors. Density 1,850 kilograms per cubic meter. High stiffness, low thermal expansion. But even beryllium has limitations. It's toxic to manufacture. It's brittle at low temperatures. It requires careful coating to achieve high reflectivity. And JWST's mirrors are small, 1.3 meters diameter. Scaling that to 5 kilometers would require overcoming enormous manufacturing challenges. And even if we could, beryllium doesn't have the radiation resistance or impact resistance needed for millions of years in interstellar space. Atlas is made of something better than the best we have. Another comparison. Carbon fiber composites used in spacecraft structures. The Parker Solar Probe uses a carbon composite heat shield to survive close approaches to the Sunday. The material withstands temperatures of 1,650 Kelvin and has minimal thermal expansion. Remarkable material. But it's designed for high temperature, not the combined requirements of high reflectivity, low emissivity, radiation resistance, impact resistance, and longevity. And it's a 2.4 meter diameter shield, not a 5 kilometer structure. The engineering challenges scale non-linearly. Atlas represents capabilities orders of magnitude beyond Parker Solar Probe's heat shield. Let's discuss metamaterials, because these might offer a path to understanding. Metamaterials are engineered structures with properties not found in natural materials. They achieve their properties not from chemical composition, but from geometric arrangement of components at sub-wavelength scales. Metamaterials can have negative refractive index, perfect absorption at specific wavelengths, or other exotic properties. If Atlas's surface is a metamaterial designed at nanometer scales but extending across kilometers, that would explain the unusual optical properties. But manufacturing metamaterials at scale is currently impossible for us. We can make square centimeters in laboratories. Atlas would need square kilometers. That's 9 orders of magnitude difference in area. The manufacturing control required is beyond conception. Now let's address the skeptical position. Could we be overestimating how extreme Atlas's properties are? Could natural materials in specific configurations achieve what we're seeing? Let's steelman this argument. Suppose Atlas is a differentiated object, like a planet, with a metallic core and a silicate mantle, but the core was somehow removed or melted away, leaving a shell. Could that occur naturally? In theory, tidal heating from a binary companion or close stellar encounters could melt a core. But the shell would be gravitationally unstable. It would collapse inward. To remain hollow, the shell needs tensile strength that natural rock doesn't have. You'd need active support, rotation providing centrifugal force to balance gravity. But Atlas's rotation is too slow for that. The physics doesn't work. Could Atlas be a fragment of a larger object, a shell piece that broke off and happens to look spherical from our viewing angle? Possible, but the observational evidence shows Atlas is not just roughly round, but apparently smooth and uniform. Fragments are irregular. They have broken edges, chaotic shapes. Atlas appears intact. Could there be a natural process we haven't discovered that creates hollow spheres? In principle, maybe, but it would need to operate at kilometer scales, produce uniform shells, maintain stability, and do so in interstellar space. No such process is known in planetary science, stellar formation, or any other field. Invoking an unknown natural process is just as speculative as invoking artificial origin. Less so, actually, because we know artificial processes can create hollow spheres. We do it at smaller scales. Unknown natural processes are purely hypothetical. Let's return to what Loeb and others in the Galileo project are investigating. They're approaching objects like Atlas with the assumption that technosignatures are worth searching for. A technosignature is any observable feature that indicates technology. For materials, technosignatures would include property combinations that don't occur naturally, uniformity that exceeds geological processes, structures at multiple length scales, indicating design, and stability that exceeds natural degradation timescales. Atlas exhibits all of these. The combination of high strength, low average density, high reflectivity, spectral flatness, structural uniformity, and million-year stability is a technosignature. It's a fingerprint of advanced materials engineering. What should we do to confirm this? First, get better spectroscopic data. Current spectra are low resolution. High-resolution spectroscopy might reveal fine structure, absorption lines, or emission features that identify material composition. We should observe Atlas across more wavelengths, from X-ray through radio. Each wavelength regime probes different aspects of material properties. Second, we need close-range imaging. From current distances, we can't resolve surface texture. We need to see if the surface is smooth at meter scales or has structure. Are there seams, joints, panels? Or is it monolithic? Third, if possible, we need sample return. A mission that approaches Atlas takes a small sample of surface material and returns it to Earth for laboratory analysis. That would definitively answer material composition questions. Fourth, we should look for manufacturing signatures. If Atlas was built, there might be evidence of the process. Variations in material properties across the surface indicating different batches or repair work. Seams where sections join. Interfaces between different material layers. These wouldn't be visible from millions of kilometers, but might be detectable with close observation. Fifth, we should monitor for changes. If the material is self-healing or actively maintained, we might observe repairs. A meteor impact creates a crater or dark spot. Does it disappear over time? That would be direct evidence of active maintenance. Let me synthesize the material's evidence into a coherent picture. Atlas appears to be a shell structure made of material with the following properties. Tensile strength exceeding 100 megapascals to resist structural loads. Density around 2,500 kilograms per cubic meter, providing mass for strength. Surface reflectivity of 94% across UV to near-infrared wavelengths. Spectral flatness indicating broadband optical engineering. Radiation resistance, allowing million-year operation in interstellar space. Impact resistance preventing visible cratering. Thermal properties enabling both heat rejection and insulation. And manufacturing uniformity across 80 square kilometers of surface. Each of these, individually, is achievable with advanced materials. Having all simultaneously in one material system is not achievable with anything we know. This is the fundamental impossibility. The conclusion is unavoidable when you look at the totality of material requirements. 3. Atlas is made of something we can't make, from a material science we don't have, through manufacturing processes we can't execute. This doesn't prove it's artificial, but it proves it's not natural in the sense of formed through random processes. It might be naturally occurring exotic matter, but that requires inventing new physics. It might be artificially engineered, which requires accepting that someone else has technology we don't. The latter requires fewer assumptions. As Loeb has stated in his work on Oumuamua and other anomalous objects, the simplest explanation is often that something is exactly what it looks like. Atlas looks like an engineered structure made of advanced materials. The simplest explanation is that it is. This is the universe of astronomy. The material evidence is clear. The properties are impossible for natural formation. The combination requires engineering. 3. Atlas was built from materials developed through millions of years of research we haven't conducted. The proof is in the properties. Properties that shouldn't coexist, but do. Properties that can't survive, but have. Properties that tell us we're looking at something made, not something born. In the comments, tell us what you think. Could there be a natural material explanation we've missed? Or are you convinced this is engineered? Stay curious, stay critical, and stay open to possibilities that challenge everything we thought we knew about what's possible in the universe.